I'm Aaron Cornelius. I'm a security researcher with GRIM. On the cyber physical systems team. We work on improving the security of embedded devices everywhere. I've also got a long background in embedded software development on critical systems, the telecom, aerospace, medical, and a bunch of different fields.
My name is Tim Brom. I run the cyber physical systems team here at GRIM. I've been at GRIM for about 5 years now, hacking all sorts of different types of embedded systems, from aerospace to automotive, heavy trucking, medical. And we're here today to talk about some of where cybersecurity meets aviation regulations. I'm going to start by talking about the current status of cybersecurity regulation and or more how software development happens in aerospace. The current process that we have descends from the historically how airlines have approached the topic of safety. Airlines have approached the topic of safety usually, historically, from a purely mechanical standpoint. This part will last for about this long in an airplane, so it has to be replaced every so often. There's maintenance procedures and airworthiness directives that talk about how often these parts need to be replaced based on how long it takes for them to fail. There's things that they test, like anywhere you have stresses on a metal joint, you'll have testing done, both visual inspection and other types of testing, depending on circumstances, to see if it's starting to fail, if it's starting to get cracks forming in those areas. But it's really designed around this concept that once you make a part, it behaves in some sort of defined way that doesn't change. Once you design it, do all your fairly rigorous testing that they do in the aerospace industry, and install it, like it will change in ways that are defined essentially by the physics of the situation. Stresses on metal, opening and closings of latches and stuff like that, that have a defined physical characteristic. And you can define maintenance procedures that will detect all of these potential issues on the airplane. The maintenance procedures are defined to replace things that you don't need to replace periodically. These maintenance procedures are, you can, followed, which in the commercial aerospace world will be followed. They rely on that happening. That does happen. And they do it in places like this. They have drawers that have labeled places for every bit, every socket, every tool. It's access controlled. So you know that when you do your maintenance procedure, there's a procedure for using this size socket to remove these bolts, and you put it back when you're done. So you don't wind up leaving a socket in an airplane. They have these fairly strictly defined procedures that you follow in order to make sure that all these maintenance is done correctly and done completely.
So that's the kind of the history of where we came from. As far as the current regulations that drive the software development process for modern aviation software, that's regulated, at least in this country and many other ones, by something called DO-178C. We're not going to go into this too deeply, but knowing how things work right now and how levels of safety are defined will help us think about cybersecurity and how to go forward with that. This is developed by RTCA. It stands for Radio Technical Commissions for Aeronautics, which I never actually knew until I looked that up. It's not super important. It's just an organization that develops a bunch of aviation standards. And again, these are adopted by FAA in the United States, Transport Canada, and the European Aviation Safety Agency, EASA. So what is DO-178C? I like to summarize it this way. You basically tell the FAA, well, a DER, it's the designated representative that stands in for the FAA. Tell them how you plan on designing, creating, and testing your software. and then you go and follow your plan and do those things, and then you have to prove that you followed your plan. That's it in a nutshell. Now there's a lot more paperwork involved. There's a lot of checklists you do have to go through and make sure that your plan actually does identify all of the areas of concern that DO 178C points out. And if the DER thinks that anything is lacking in your plan, they will tell you and help you and make sure that it gets revised appropriately. That's the way things go forward right now.
And as you can see, it's kind of a very waterfall-y based model where you do all your design up front, you create a design, you create a spec, that actual product that implements the design, then you do testing on it in order to make sure that the product design actually meets the requirements that the product was supposed to fulfill.
That is a good point. The way this does work in practice, it is extremely waterfall. There's been attempts to try and figure out how to fit agile methods into this, but it is very much plan, do, prove, just pretty much in those steps.
And this, again, comes from that historical background of making mostly mechanical components, where that is how you design them. You don't do iterative development on a wing, usually. I mean, if there's issues, you'll go back and fix them, of course, but like you don't really do, there is no fail fast on making a lot of these mechanical components. So it's trying to shoehorn software development into how they make mechanical components for these aircraft.
Right. And as anybody who's been in software development for a while knows, that waterfall has been around for a long time. The D178C categorizes different levels of software according to the potential consequences of a failure of that software. So levels A through E, and basically A means that something catastrophic would happen if it fails. Level E means that nothing is going to happen safety-wise. Maybe the passengers can't watch movies, right? That would be a level E software. The level A is also the highest cost. This is probably unsurprising. The last numbers I could find showed that it's estimated to be about $100 per line of code for level A software. They're not all software on an airplane is level A. There's usually just as small a percentage as possible because of the cost. But Boeing 787, for example, is estimated to have between 6 and 7 million lines of code. So even if it's a small percentage, just the level of certification alone of the software drives a great deal of cost. Basically, these go from different levels. So level A, catastrophic. Software that is level A rated will have autonomous control, which means that there's no way to intervene if something fails, hence why it's so expensive and so time consuming to develop. Then they go on below there. Level B would be something where something hazardous could happen, but also level B will typically allow for pilot intervention. So it might be something that significantly increases the workload or the challenge of flying the aircraft, but it would be something that can be addressed by the pilot training.
The between A and B is usually loss of life. Like a level A failure was likely to lead to loss of life. Level B failure is not likely to lead to loss of life or severe injury. Injury sustained in a level B failure should be minimal.
Yeah. And then it goes on down from there. C and D are major, minor impacts to the flight of the aircraft. Also, so entertainment systems are going to be level E. Means that there's less regulations and less checklists, essentially. As you go down in level, you have to do less to prove in that prove step. So,
there's some stuff in DO178C. Code is expensive, so stuff, especially at the level B or level A, is very unlikely to have unused code in it or unnecessary code in it, like a shell onto a system. It's Actually, D178 level A, you're not allowed to have dead code in your design on the system. So there's because it's so expensive to develop the code, there's usually a minimal amount of code on these systems. There is extensive testing done especially for the higher certification levels. There's at least a significant quantity of testing done. Pilot training on how to use the software is, the other systems are designed for redundancy and safety. So if you do have a failure, there should be a redundant system to back up that failure, unless you're the 737 MAX, but we won't talk about that right now. There's also very, very limited interfaces on these flight critical systems. They use interfaces like RINC 429. RINC 429 is a UART style bus. You're limited to sending 32 bits of data at a time. So there's not really room for buffer overflow here. You don't really have longer messages on top of RINC 429. These interfaces are very strictly defined and fairly limited, provide very limited functionality beyond just sending the necessary critical data back and forth on the bus.
Yeah, there's a great deal of emphasis on determinism and reliability.
Yep.
So, there's some bad things related to the current way software is defined and designed in aerospace. This is kind of, so as I said, as we said, both Tim and I have worked in aerospace, kind of on the development side of things and also on the cybersecurity testing side of things. The things that I found many things frustrating when I was doing on the development side of things. This is kind of a piece of that list right here. Data validation is guarding against accidental data modification. The design of how software is made to be robust in aviation systems is guarding against like cosmic ray bit flips, single event upsets. So simple methods like CRCs and checksums are sufficient. And also the hardware that runs it is typically slower and older, more reliable, and therefore modern data validation methods can be very time consuming for those, for the hardware involved. There's very little code to guard against unexpected scenarios. If every single line of code costs $100 approximately, it's probably more nowadays than it was when I found that statistic, then you're not going to have a bunch of code for guarding against things that the system designers say won't happen. In fact, as Tim says, dead code that is never expected to be executed, is not allowed in D178C. There's a lot of complacency because of the level of tests involved, because of the amount of work that goes into designing the software. There's a lot of point of view in the industry that the way we do things, the redundancies that we design into the system protect us from bad things. And it protects against single event upsets. It doesn't protect against determined and directed attacks.
One thing, one piece of software I was working on a while ago had just a straight up buffer overflow attack against it. And I had to fight fairly hard to actually get it fixed because the incoming data that hit that function with the buffer overflow could only come from a trusted source that would never send more than such amount of data. And if there was some sort of, like Aaron says, a single event upset, some sort of real random bit flip that caused the length field to be longer than it was supposed to be, there's a CRC check that would have failed and they wouldn't have even processed the data at all. So they felt that they were completely protected against this scenario because they just don't have this concept of an adversarial attacker with knowledge of the system being able to get data into this function. They believe that the only way for data to get into this function is from a source that they trust to not send data that's going to cause a buffer overflow.
So Tim's kind of jumping ahead there. That last bullet point on this one is software is only tested against expected flight configurations. So you will only say, here's, this is what we're going to do for this flight, and that's what we're testing because testing is expensive. There's a lot of tests that are performed as part of this software certification process. You don't want to run more than necessary. What that means, though, is that aviation software, while robust in flight configurations, can be extremely brittle when it is put into conditions that it is not that are not expected to happen. Some other things here: ground maintenance devices, so things that actually program the different flight devices. Those are not DO-178C rated because they're not flying, right? They just stay on the ground while the airplane flies. They're covered under some different guidelines about tool development, but they don't have to go, they're not even level certified. It's something different. Maintenance software, so on each box there's typically a component that will help reprogram that device. That's considered to be deactivated because when the airplane is in flight, you have a signal that says, are the wheels on the ground or not? Sometimes it's called weight on wheels, sometimes it's called weight off wheels. Make sure you read your documentation very carefully. And whatever signal that is indicates if that signal is then used in the startup process to make sure that the reprogramming software component doesn't run. So this is considered to be deactivated.
There's also frequently a physical switch on the piece of hardware. They have to switch into some sort of boot mode, maintenance mode, programming mode.
Right.
So you have to not only have the weight on wheels signal, but you also have to have this switch set in the activated position to boot the piece of hardware into the maintenance mode, and then the plane won't fly if that piece of hardware is in its maintenance mode or programming mode. You have to switch it back to flight mode before the plane will take off.
Right, and it'll be like programmed in, sometimes they're built into the wiring harnesses themselves. So when you plug in the harness for reprogramming a box, that thing has a little wire jumper in it that forces this type of mode.
So there are some current cybersecurity documents out there, DO-326, which DO-326 which outlines the activities that should take place at a system and airframe levels. These are the type of security activities that you should do if you're developing either a system for an airplane or developing the entire airplane. These are the various testing activities and testing documents that you should create and how to create them. DO-356 goes a little bit more into the nuts and bolts of what testing should look like. Something I like about DO-356 is DO-356 does make provisions for the more ad hoc pen test style testing that hackers tend to do. The adversarial feeling around, trying to see, scan different systems, trying to find some way in, some chink in the armor that you can then exploit and get into the system. This is a testing that's most testing that you see, especially the DO-178C type testing, is extremely formalized. Every test procedure is written down. You do this set of procedures. This is your test. There's conditions for the test to pass. There's conditions for if they don't meet the passing conditions, the test failed. DO-356 does give those provisions for the more ad hoc style testing that can be much more useful for security testing. Provisions for things like fuzzing, which doesn't really have an analog in like DO-178C, because you can't really formalize a fuzzing procedure.
So that's where we are right now. We've got some concerns with the current way aviation software is currently defined. What do we do? So what do we do about that? Well, Tim and I have a plan. First, as with anything, we've got to figure out what our actual goals are for what needs to be secured, what devices need to be secured, and come up with some examples, come up with some measures that we can use to reach those goals. It's all very well and good to say, secure the system, but if you don't actually tell people how to go about doing that, you're going to end up with a large number of ways to do that, some of which may not be very effective. So the problem is up front here, everything is hackable, right? Give in enough access, motivation, time, and money, you can get into any type of device. You give us a piece of hardware and we can get into it. There's a lot of measures you can use to make it more difficult, but with a large enough playground, you can get into anything you want. So for goals here, we need to assume that an attacker has all the necessary information and resources to do what they want to. If we're going to design an aircraft to be secure, we need to start from the assumption that the adversary knows what they need to know to get into it. We need to make sure that we have some way to prove beyond the most up-to-date way to prove that the software on a particular component is 100% correct. If you cannot prove that, then it's going to be impossible to figure out how to get to secure an aircraft. We need to prevent accidental transmission of something malicious. If you know that everything is secure at some point of time, you need to, protect it from going forward, and then put multiple barriers in place also all these different components. We know that given enough time and money and so on, anybody can get into a device if they want to. But it is possible to figure out how to make an attack practically impossible if you limit some of those things. So if you know when an airplane's on the ground that it has all of the correct software and configurations in all of the different parts that are on the aircraft, then an attacker would have a limited time frame of the actual flight itself to perform an attack. So that's what we're aiming for.
And also aiming to get the idea into aviation that a software component can go from good to bad very quickly. Just one exploit, and all of a sudden this device that was working completely fine is now no longer working completely fine, and it's not based on some statistical degradation over time. Now that can just go be good and then be bad.
So to define what is important to secure, here's my list. We have things that are important for flying an aircraft, and then we have things that are not important for flying the aircraft. These are two device categories. The level D178 levels, or D178C defines 5 different levels of how critical software is and the consequences of failures here. For us, there's really only 2 categories, important or not. Because if you leave something that has partial measures in place on the aircraft, then that is a potential point that an attacker could use to pivot to other parts of the aircraft.
Flight devices are any component that's used to operate the aircraft. Any device that communicates with those components. We've seen instances where you may have a level E hardware device that communicates in some way with even a level A hardware device. And this is allowed because that communication has been strictly defined and tested on the piece of hardware, the level A software, to make sure that it should reject any bad inputs, with oftentimes not very robust checking on what these bad inputs actually are. But from a security context, anywhere that you can touch something important from also needs to be secured, because if you can have a lower functioning device, a lower classification, lower D178C DAL classification device that can maybe in some way disrupt a higher level, more critical device. And this is something that you have to think about from the security perspective as an attacker, using this as a potential pivot to get onto a more critical system. And also any device or software that interacts with these components, whether in flight or on the ground. All of your ground maintenance software needs to be considered essentially from a security level the same as a flight device, because these are things that are designed to be able to modify the behavior of these pieces of hardware in flight that are responsible for directly controlling the flight of the aircraft.
And I think that's an important point of what we're defining here. Things that we consider flight devices includes the things on the ground that program the device, because those are very critical to making sure that the correct and only the correct components are programmed. You know, one thing also, Tim talked about the different components, different level of components talking together on the same bus. One very common level A software item on recent aircraft is an operating system running on a particular device. There is a standard called ARINC 653, which defines ways for a partitioned operating system. It's effectively like a virtual machine, can have multiple different severity levels running on the same component. So as we all know in security though, virtual machine escapes are definitely a thing. So if there was an attacker who was able to get into a lower level component, you know that they would be able to, from there, pivot into the operating system itself or a more critical component if they wanted to. So that's our devices. How do we go about doing this? Well, we've got a couple different things here.
So there's adversarial testing. I choose the word adversarial testing because I don't want to say pen testing, because pen testing means different things to different people. This is the idea of attacking the, testing the system as an attacker would. You're no longer just strictly checking against a specification. You're actually looking at it from if I was an attacker, how could I leverage this system to do something? How could I abuse this protocol to do something? All the things that security professionals that we do in our jobs. How do we doing these things to now an airplane? Another method is some sort of pre-flight software and configuration authentication. If before every flight there was a way to go and check that the system is actually running the software that you think it's going to be running, actually has a cryptographically secure method of validating that the software that's running is the software that's supposed to be running, that your configuration is correct. Other methods could include like physically incompatible interfaces on flight systems to make sure that no flight system, you can't just plug your iPad into a critical flight system, that there's the interface on these flight systems, just they don't speak these commodity protocols like USB or Bluetooth or Wi-Fi. We'll talk about this a little bit later. We also need to talk about air gaps. I know anybody in ICS is definitely laughing a little bit right now, but on an airplane with a strictly controlled configuration, air gaps could certainly be a part of the solution for making sure that you can't jump from, the non-flight critical portion of the aircraft to the flight critical portion of the aircraft, at least as a passenger sitting in the plane.
Sure.
Now, the adversarial testing, review and test all interfaces for vulnerabilities. You have to, you can't just blindly trust the external inputs into the system, even if they should only be coming from a system that's also been tested to the same level and should only be producing correct outputs for you to consume. You still can't trust this because you can't always trust that the system hasn't been compromised in some way.
I like to give an example from automotive for that. If you have one component that tells you the brake is pressed, and you make sure that the thing that actually generates the signal saying the brake is pressed works perfectly, can't be cracked. The thing that interprets that signal works perfectly, can't be cracked. It's all well and good, but if you then have an entertainment system on the same bus, and that sends a message saying the brake is pressed, well, now you can't trust your inputs, can you?
Yeah, and testing your protocol stacks and messages, your vulnerability. I mean, we've gotten a little bit better, but there's been lots of vulnerabilities found in TCP/IP stacks and other network stacks over the years. Reviewing the software and compile code for vulnerabilities, making sure you're doing like static analysis on the code. Not a perfect solution, but it does catch some things. Secure boot is, I think, a fairly critical part of making sure that we can actually trust the software running on these systems. Having a good secure boot platform set up could go a very long way to preventing at least an attacker from modifying the operating system. That should then be modifying the software that runs on this platform, because it should be detected. And of course, having multiple layers of protection. Defense in depth has always been one of the strongest things that you can do for the security posture of basically anything.
The topic of secure boot is one that could be talked about for a long time, and different people have different definitions of what secure boot means. At a simple level right now, I think what we mean is just that there's a way that the hardware has the ability to use cryptographically secure methods to ensure that only authorized software and components are installed and operating on that device.
And a way to store the keys that should be immutable.
Right, and also should not, once somebody gets in and pulls apart the hardware, that they are not able to go in and break the secure boot for all of the devices, right? Something that is uses perhaps asymmetric cryptography methods and secure hashing to do.
Keys per device.
So pre-flight software authentication, talked about this a little bit earlier. We want to make sure that before takeoff, that everything on the aircraft is 100% correct and secure and authentic. So this would be some centralized way to query every single device and find out what software and configuration are running on them. This is already somewhat in existing, before an aircraft flies. This is already somewhat what happens, right? We need to make sure that only the correct software is on each component. So people who fly aircraft will already have a list of different software versions that should be running on each component of the aircraft. So this isn't as outlandish as it sounds. They use cryptographically secure algorithms, no CRCs, no checksums. You should be using something like SHA-2, SHA-3, something better. And it should be also the protocol, the way the centralized device queries every single component. There should be a challenge response protocol here. The protocol should also be tested adversarially to make sure that it is something that cannot be spoofed. We need to make sure we can prevent replay attacks. So if there is some malicious software, malicious component on a box, it should be incapable of falsifying the authenticity of that software. And also validate the entire range of memory and flash on each device. You want to make sure that you can't set the length to 0. You want to make sure that you don't have the correct software and the correct configuration, and put some sort of mystery component in the middle, and that gap just isn't checked because it wasn't thought to be important, right? You need to make sure that the entire range is validated.
Yeah, physically incompatible interfaces. We're seeing the flight crews. They have the iPad devices that will be their flight book that has the flight information. One of the ways to make sure to help prevent malicious software from being loaded onto these flight critical systems is to make sure that there are physically incompatible interfaces between the non-flight systems and the flight capable systems. So your flight capable systems shouldn't have USB, they shouldn't have Bluetooth, they shouldn't have Wi-Fi, they shouldn't have these standardized protocols that everything speaks. Specialized hardwired connections, like the connections we have a picture of here, very common in aerospace, just make it a lot harder for the flight crew to just plug their iPad into a flight critical system.
And if you can see on these connectors, some of the important parts of them is that they've actually got different keying. So there's usually a bunch of different, pins, so that you have all the necessary signals that you need for a particular connector. But then there's a lot of different varieties of keying. Maybe some have 5 slots, some have 4, different widths, different positions. And the whole idea is that you want to make sure that you cannot connect a component wrong. This is already what's done on an aircraft for connecting all the different flight components. And this is something that we say is necessary when connecting anything to a flight system. So air gaps, as Tim said, everybody who was in ICS is probably laughing when we had that up there before. But the whole point is that an aircraft doesn't change. If it changes because the design of the aircraft changes. It changes because there was an actual documented and tested reason for doing so. So designing the system, you should make sure that the flight systems and the non-flight systems cannot talk at all. They should be physically separate. As I said, virtual machine escapes are definitely a thing. You should not be running on the same box. They should not be able to even talk on the same bus. So anything that needs, if somebody, you don't want to have to test everything on an aircraft, right? You want to make sure you can, you want to try and trim what you need to test because testing is expensive. So something like an entertainment system. Maybe somebody doesn't want to go about testing that. Well, that's okay if you can make sure that that entertainment system can never ever talk to a flight system, which means no common buses. It means that the only thing on the aircraft connected to that entertainment system from the flight components is power. If you need somebody to, if the crew needs to like disconnect a component, they would need to be able to, toggle the power to that device instead of actually sending it a message to shut down. So some examples of what we've got here. We're going to go through some different category areas, 3 different types of systems, and talk about how we would apply these things to ensure that they're secure. Maintenance, and these cover, this is pretty much the, all the different types of devices that you would have then on an aircraft, right? Passenger accessible systems, the things that passengers can get access to, and so on. So maintenance devices, these are the things that program the different components when the aircraft is on the ground. They usually a fancy laptop, maybe a robust laptop with some sort of waterproof case and special cables and extra interfaces to talk to the aircraft parts. These need to be adversarially tested. This should be unsurprising to hear by now. Communications with the different flight devices should require full authentication, and these devices should also have a plan and method to periodically validate that the device itself has not been compromised. As I said, they're typically a regular laptop or some sort of PC type device. So any of the standard ways to secure a PC, a laptop should be used on these devices to make sure auditing, they should have auditing on, you should have all the different security protections in place. Programming other devices as well is typically, it can happen through, there is an ARINC standard for this as well, although it's optional. Not every device implements it. It's called ARINC 615 for data loading. And that could happen over multiple types of device buses, such as ARINC 429. These devices will then usually talk over that. It's kind of a double-edged sword. On one hand, it means it's you've got a standard way of doing things. On the other hand, it means that if somebody implements ARINC 429, you potentially be able to go up and program with an unauthenticated device, which is why communication with the flight device should require full back and forth challenge response authentication on both ends. The device should make sure that the device programming it is who it says it is, and vice versa.
full mutual authentication.
That's the term.
So passenger accessible systems should either be incapable of connecting to aircraft systems, not physically connected in any way, not physically sharing any, any piece of hardware. Ideally, not even speaking the same sort of protocols, so they couldn't even accidentally be connected together. You can't just plug the USB into RN429 and have it work. Or they need to be, same as everything else, adversarially tested and not have external connectivity that a normal passenger would be able to just plug into and use. If you have like a USB for charging, it should only be for charging. Only the data line should be connected. It shouldn't have any of the you should be capable of passing data back and forth.
The only case where there's an exception then is if this is a system, if the entertainment system is incapable of being connected to critical flight systems or to flight systems, then you could have a USB audio interface on it.
Yes.
But that's the only case where that would be allowed. You would need to make sure that this device cannot talk to anything else. And the whole goal here is to make sure that something can't be done, something cannot accidentally or through, through somebody dropping a bad cable somewhere near the airport, have somebody connect something that shouldn't be connected to the flight systems. That's the whole goal here. If somebody is going to try and attack an aircraft during that limited window of the flight itself, we want to make sure that it is incredibly obvious that they're doing something that they shouldn't be doing. So just plugging a USB in is very benign. But if they're starting to rip up panels and trying to find the Air 429 bus somewhere down there, well, that should hopefully be obvious to some of the other passengers or the crew, and corrective measures can take place. But that's the whole goal here. We want to make sure that it can't be done accidentally or on purpose without it being obvious. So the flight systems themselves, we've talked about these quite a bit already. These need to be adversarially tested, of course. We need to make sure that there's multiple levels of, there's multiple layers of protection in the way for anybody who is trying to attack a system that they would need to get through. No consumer interfaces. So all those flight systems, you need to make sure that you do not have the, there's no USB in there. There's no Wi-Fi in there. So iPads as a flight bag are a thing now. And obviously there's an appeal in terms of how easy it is to update. You don't have to carry around stacks and stacks of paper. It's an easy way to store a lot of things. But that means you've now got a device which is in the cockpit, which is considered a flight critical system, which is a consumer device. And that gives me some concerns. So I think there needs to be some thought on how to secure that type of system. Maybe it just needs to be not an iPad. Maybe it can be a special purpose device. There's plenty of things out there with an LCD that can store maps and have a program in them. No consumer interfaces, yeah. So no USB, you wouldn't be able to connect this. You don't want to have somebody accidentally plug in a USB that they're not supposed to, right? So just as a quick summary here, again, our goals, these are the things that we want to achieve. And I think we have for what we've put in place. Making sure we still have to assume, again, that's upfront, an attacker has everything, knows everything. We've talked about providing a way to make sure that the systems can be validated to be correct, that the software and configurations on the different components are correct when the aircraft, before the aircraft takes off. We want to limit that potential attack window. We've talked about the ways we can prevent accidental transmission of something malicious through the physical, air gaps, physical disconnects, physical incompatible interfaces. And then again, if this is all, the goal is make multiple barriers there. Multiple barriers there an attacker would need to get through.
Yeah, and then 2 device categories. There's stuff that can affect flight and stuff that can't affect flight.
Yeah.
And can't affect flight does in this case mean full physical isolation from anything flight critical.
Methods, we've talked about these at length. Adversarial testing, I believe, is a key part of this. One thing I guess we didn't really talk about is kind of design standards. It's something that could be addressed as well. Making sure that the software as it's developed complies with the different best practice recommendation of how to develop secure software in terms of like program functions that are allowed and such. That's another potential method. We are more looking at the fitting things on top of what was there already. But we still do have a few problems that we need to solve. So we're not going to try and pretend that we solved everything here. We'd like to think that we solved a significant part of aviation cybersecurity just in this talk. But there's a few things that we need to think about going forward. Supply chain security is still a concern. Obviously, as I said, anything can be hacked. As the devices are sitting in storage, an attacker could go in and modify them. They've got plenty of time to go in and modify them, figure out how they work, either modify the software or just physical modifications to the hardware in them. And how to make sure that that doesn't happen or can't happen is a challenge.
RF communications is also another area where that would really address. The airplane has a fair bit of RF communication, that it has radio, ADSB, weather, etc. This is also something that isn't addressed by this what we've presented here in this talk.
Yeah, I mean, the flight crew, the pilots training is a significant part of that. If there's issues with communications between the aircraft and the ground, that's something where training can kick in and deal with the situation. But it is still something that it would improve matters if there was a way to secure the communications. Things that we might also want to think about in the future: how much change would require something to be retested, more adversarial testing. What level of change, what type of change? DO-178C defines that for software, where different amounts of change are considered to be minor fixes, and they don't have to require a complete redesign of the system. But some level of change does require complete redesign and retesting the system. So that's something that would need to be looked at in the future. And then there's also the maintenance devices themselves. We talked about how maintenance devices are used to program all the different components on an aircraft. This means it would be used to program both flight systems and these air-gapped non-flight systems. So maybe those need to have a slightly different category. You can put together a committee meeting and argue about lots of this stuff for a while if you want to. But I think that what we've given here is a fairly complete approach to address cybersecurity. Any questions?
We'll be in the Discord for any questions.